This is the quadratic formula. It allows us to find the solutions to quadratic equations. How is this derived? The basic principle is transforming the quadratic equation into a perfect square. It's an algebraic proof. However, have you ever seen a geometric proof for this formula? It helps visually understand the meaning of the quadratic formula. Let's math travel. What does it mean to solve this equation geometrically? It means finding the x-coordinates of the intersection points where the graph of the left-hand side meets the graph of the right-hand side. The number of intersection points is the number of real roots. The graph of y equals 0 is the x-axis. Since this is a quadratic function, the graph is a parabola. If a is greater than 0, it looks like this. If a is less than 0, it looks like this. This graph is symmetric around this axis. It is the axis of symmetry. Let's deal with the case where a is greater than 0. Since the quadratic formula binds two real roots, we consider the case where the two graphs meet at 2 points. The x-values of these points are p and q, with q being greater than p. We need to find the values of p and q, which are expressed in terms of a, b, and c. It will be the same result the quadratic formula gives us. This parabola is symmetric about this axis, so these 2 points are also symmetric around this axis. This length and that length are the same. P is x-value of the axis minus this distance. Q is x-value of the axis plus this distance. This distance is half the distance between the 2 points. Since the distance between q and p is q minus p, this distance is q minus p over 2. So, p and q are expressed like this. In order to express p and q in terms of a, b, and c, we need to find the values of the axis and q minus p. The axis is at the midpoint of these two intersection points. The x-value of the axis is p plus q over 2, so the values of p and q are rewritten like this. We need to find the p plus q and q minus p. How can we find these values? It seems like the problem has gotten more complicated, but we can easily find these values. Do you remember the relation between the roots and coefficients of quadratic equations? The sum of the roots is equal to this value, and the product of roots is equal to this value. Applying this relation, the x-value of the axis is this. Substitute this into x of this function. That value is the y-coordinate of this vertex. The coordinates of the vertex are like this. The value of q minus p is left. Let's use this multiplication formula. Substitute p plus q and pq into this formula. Simplify the equation. The value of q minus p is this. Therefore, p is this, and q is this. Combining the expressions into one, we get this. This expression matches the quadratic formula exactly. As shown in the formula, the number of real roots, which is the number of intersections of two graphs, depends on this value. If it equals 0, there is only one real root. The two graphs intersect at only one point. If it is greater than 0, there are two real roots. The two graphs intersect at 2 points. If it is less than 0, there are no real roots. The two graphs don't intersect at all. This is the geometric proof of the quadratic formula. Good job!